All right, physics students, here we go. Newton's second law lab. This is the second half of the lab. This is the data analysis, all right? So you got the raw data over here. I got a calculator ready to go, all right? Again, the purpose of the lab is to determine the relationship between the force acting on a system and the resulting acceleration of the system. Now, a couple things we had to do, though, is when we ran the lab, we moved the mass from the cart to the hanging part, right? So the whole mass of the system, the mass of everything, stays constant. All right. So if we're keeping something constant in a lab, we want to record that, right? You want to record as much stuff as possible. Maybe I should have recorded the length of the track, the height of the fall, um, anything you can measure, you probably should measure in a lab setup, right? So these labs we do, they're very open-ended. Now, there's some that are fill in the blank type labs, right? So in physics H, you got some labs where it's friction lab, fill in the blanks. The gravity lab, we filled in the blanks. We haven't done a write up for the last couple labs. Um, so this one is a classic kind of write-up lab, and actually probably the next write-up lab we'll do in Physics H as well. I repeat this lab in Physics C for those kids that don't have me as juniors because it's a really important lab. It's a really important lab to set this up and do this, and kind of reinforces a couple things, right? The acceleration is slope of the velocity versus time graph. So I don't have one on here ready to go, but I kind of sketched out what it looks like to find the slope of the acceleration versus time graph from the motion detecting, and that is how I recorded these accelerations. All right, and actually I ran these both twice. Actually, I think I stopped running twice somewhere around 1,330 grams. This column I generated in Logger Pro, so I show you how I did this. So I figured out all the total mass we had, or I had. This is my own setup. Um, it would be different, might be different depending on the cart you use, right? If you use the blue cart versus the gray cart, they have a slightly different mass. You'll have to figure that out on the spring scale. This would be the same for everybody if you use all four. The hanging mass could be different for people. The shield should be about the same mass. So I had a total of 971 grams or 0.971 kilograms. Then I started changing the mass that was hanging off the side. And I took the masses again, all the mass, little brass discs I had on the cart, and then I transferred them over as we went. So the one thing we're going to do here is we are going to break the rules of graphing a bit. We controlled the force acting on the system and measured the acceleration. So typically, you put the acceleration on the vertical axis, all right, and you put the force on the horizontal axis. It's a fine thing to do. In fact, we might keep it that way in Physics H, but I'm going to solve it. I'm going to write it a little bit differently. I'm going to write it as on the x-axis, I'm going to put the acceleration. So again, this is breaking the rules a bit, but I know what form this equation should take. So the most useful form it should take. So I'm going to write it like that. So I'm going to call it the net force. I'm going to call it F net. Units for force are newtons, right? So we got that by taking these and multiplying. Actually, hold on a second. This is the x-axis. My bad. This should be the acceleration. A units meters per second. I'm going to square it with a superscript. Square, meters per second squared. My bad about that. And then the y-axis is going to end up being net force. But first, I'm going to put it the hanging mass. All right. I'm going to use a calculated column to calculate it because, well, I'm going to be a little lazy. Actually, it's not lazy. It's a good way to do things, right? Because there's some kids who calculated this by multiplying the mass by the acceleration. You can't do that. You can't use one of the data you collected on one axis and then use it in the other axis. It ends up being a perfect fit, and it's not. It really means nothing. So what we're going to do is data, new calculated column, and this is going to be the F net. This one's going to be the net force. All right, F net. Units here are going to be newtons. The expression is going to be variables, hanging mass times 9.8. I did 9.81, which really doesn't make sense. Now, nothing's in there yet. Now, it's a little bit hard to see, unfortunately, because I have Logger Pro. When you shrink it, it makes this almost impossible to see. Oops, and look at that. I have the wrong unit on here. I have meters per 2. Whoops. Maybe some of you noticed it as I was doing it. All right, 0.52, 0.72, 0.93, 1.12, 1.35, 1.55, 1.66. I'm using the number pad to quick enter those and then put the arrows down. Now the mass is 0.05, 0.07, and notice it automatically starts calculating the information there, the net force. So I've got all that. My line's down here, so I'm going to do a right-click auto scale from 0. All right, I'm going to throw a fit line on here. Beautiful fit line, beautiful fit line. Actually, this came out a little bit better than when I did it before. I wonder if it's because I used 9.8. All right, I'm going to maximize this so we can see everything a little bit better. All right, so that looks a lot better. So the slope of the line, we have to change this to net force. All right, now I put the fit line on it. All right, so there it is. Actually, so it ends up being about the same. Net force versus acceleration in meters per second. Perfect graph. Go ahead, print it. Now the equation for the line, your experimental equation. All right, I'm going to write it on paper and hold it up here for you. I tried doing something different with like the camera pointing down. I guess I could just point the camera down and write on paper, but I don't feel like moving the camera. I'll just hold it up. So the experimental equation here, we have, make sure I have some bigger paper here. We have F net, all right, equals 0.94 newtons per meter per second squared times the slope of the line is A. So there's your experimental equation. I got to cover my face to be able to see this. All right, there's your experimental equation. Now, the slope of this line, what does this mean? It always means something. So I'm going to tell you right now, a newton is a derived unit, right? So we always start by analyzing what the slope and y-intercept here. The y-intercept is 0. I'm not even going to leave it. I'm not even going to put anything on there. Look at that. It's a great slope. That's a great y-intercept, nearly 0. So when we start analyzing the slope, first thing we do is analyze the units and try to see if we can make sense of what the units mean. So newton per meter per second squared. Well, 1 newton, all right, 1 newton is equal to 1 kilogram times meter per second squared, right? So you don't know that yet. This is your first indication of what a newton might be. So 1 newton is a kilogram times meter per second squared. So if you divide a kilogram meter per second squared by meter per second squared, the meter per second squareds cancel and you're left with kilograms. Cool, man. The slope of this line is a mass. All right, so what mass is it? Well, it should be pretty obvious here that the only mass it could be is the one we measured. It's the mass of the system. It's the mass of the system. If we go back and look at this, right, check this out. Move my face. 0.95 newtons per meter second squared, that would be kilograms. So F net equals 0.95 kilograms times A. Look at that, 0.971 kilograms. So that's not too far off, right? What we usually do is we find the percent difference of the numbers, right? Or percent error. The theoretical value here should be 0.95. So diff or error. Error is a little bit different. So percent difference, right? It would be 0.971 minus 971 minus 0.9. I did 2 sig figs here on the slope because I used 2 sig figs. So, you know, 0.94 I used here. I used 9.5 there. I think if you use 9.81, it rounds up to 9.5. So I'll make it 9.5 here, I suppose. So 0.97 minus 0.95 is 0.02. 0.02 out of 0.95. Got a little calculator app here, ready to go. 0.02 out of 0.95 is about that, times 100, it's me about 2%. It's about a 2% difference. That's awesome. So the slope of the line ended up great. The difference between the theoretical and the experimental. So the slope of the, I ran out of good paper here. The slope of the line is mass. The final general equation ends up being F net equals the mass of the system times the acceleration of the system. F net equals ma, which, if we had plotted it the other way and put a on the y-axis like we should have probably for the rules of graphing, right, you also get a linear line, right? But the slope of this ends up being 1 over the mass. So it ends up being F net over mass, which that's hard to recognize. If you plot it like this, it's hard to recognize that this ends up being 1 over the mass because the units come out being 1 over kilogram. I mean, you can recognize it, so it's inverse of a mass. You'd have to go and calculate 1 over 0.971, the theoretical value there, and go from there. All right, so kind of summarize, the acceleration is dependent on the mass of the system and the net force. So as the mass increases, as the force increases, the acceleration increases. Now, the slope of this line, if it was a bigger mass, right, the slope of this line would actually go down because it's inverse mass, right? Less acceleration with more net force if the mass of the object increases. If you go back to net force and acceleration, they actually flip. The more mass there is, the steeper this slope would be because its mass is in the numerator, and therefore means it would take more force to get the same acceleration. Like if you wanted 1 meter per second acceleration, for this mass it's this, but if you had more mass, the slope of the line would be steeper, so that means it would take more force to get that same acceleration. All right, so pretty easy write-up. You got videos of the setup, videos of data collection, videos of everything. My kids were griping yesterday that I didn't get the videos up early enough for them when they're on remote day, which I sort of don't buy. I can't imagine these kids are getting up at 8 and actually doing their work. But anyway, it is what it is. So I'm trying to redouble my efforts, make sure stuff is up and updated first thing in the morning if I can. So yeah, here's your video. Enjoy, be good, have fun, write the lab up on your remote day. Should be a quick write-up. I'll make it due next week, Monday and Tuesday. All right. If you're not going to be here, you can submit it digitally.